We are in section 3.3, measures of relative standing and box plots. The first definition that we have is a z-score, and we will see z-scores being used throughout the remaining part of this semester. So a z-score, or a standard score, or a standardized value, is found by converting a value to a standardized scale. Is the number of standard deviations that a given value of x is above or below the mean. So a population z-score and a sample z-score are calculated the same way, however using population data and also using sample data. So to find our z-scores, we take our value, subtract the mean, and divide by the standard deviation. We have a list of important properties of z-scores. The z-score is unitless and it has a mean of 0 and a standard deviation of 1. This is really important. If the data value is larger than the mean, then the z-score is going to be positive. And then if the data value is smaller than the mean, the z-score will be negative. A data value is significantly low if the z-score is less than or equal to -2, and significantly high if it's greater than or equal to +2. The z-score provides a way to compare apples and oranges, different data sets, by converting variables with different means and standard deviations to variables with the same mean, 0, and standard deviation of 1. That way we can easily compare them. We typically round z-scores to 2 decimal places unless otherwise stated. We have an example that says a student takes 2 exams, getting 55 on test A and a 60 on test B. The class scores for each exams are normally distributed or bell-shaped. For test A, the mean is 50 and the standard deviation is 5. For test B, the mean is 50 and the standard deviation is 12. Find the z-scores for the 2 data sets and compare them. So in order to find our z-score for test A, we need to take our value that we received on this exam and the student scored a 55, and we subtract the mean, which was 50, and then divide by our standard deviation, which is 5. Working this out, you would have 5 divided by 5, or just 1. Z-score for test B. The score on test B that we received was a 60. Subtract our mean, which is also 50, and then divide by our standard deviation, which is 12 for this one. So we have 10 divided by 12, which is going to work out to being 0.83. So both exams, the student scored above the mean, since these are positive z-values. It also says below this, says the z-score for test A is blank, then z-score for test B, and this means. So looking at the z-score for test A and the z-score for test B, you can see that A is greater than, so it is larger than that for test B. And this means that the student did relatively better on exam A. This is also used when a lot of times students are applying to colleges and they have to submit either ACTs or SAT scores, and they might take both, and then they calculate these to see relatively which one they did better, and then apply with that score. So we can use z-scores to identify significant values. We saw that earlier. And so again, with our z-scores, the mean is 0 and our standard deviation is 1. So extending out 2 standard deviations to the right would be at 2. 2 standard deviations to the left would be -2. So significant values are those with a value of z less than -2 or greater than or equal to +2. And again, that's significantly low values and significantly high values. The example right below says the weight of kittens is roughly bell-shaped or normally distributed with a mean of 3.6 pounds and a standard deviation of 0.4 pounds. The weight of Maria's cat is 2.7 pounds. Is this value significantly low? So a way to figure this out is we can calculate that z score, and if it is less than -2, it would be, or equal to -2, it would be significantly low. So our z-score here, Maria's cat weighs 2.7 pounds, subtracting away the mean, which is 3.6 pounds, and dividing by our standard deviation, which is 0.4. I'm going to round this 2 decimal places. When you do, you get -2.25. And so yes, this is smaller than -2. So yes, this weight is significantly low. And the reason why is because it is smaller than or equal to -2. Right below this, we get into kth percentiles. This is denoted P sub k, is a value of data set that splits the data into 2 parts. The lower piece contains k% of the data, and the upper contains the rest. So 100 minus that k%. So k can be any value between 0 and 100. 50th percentile is the median. Many exams use percentiles to let students know how they scored on their exam in relation to all other students who took the exams. In order to figure out the percentile of a value of x, you're going to take the number of values less than x, and that key wording here is going to be less than x, and then divide by the total number of values, and then multiply by 100% to get that as a percentage. And then a lot of times they're going to have you round to the nearest whole number. So the example right below this says, explain the meaning of the following percentile. The 5th percentile of the weight of males 36 months of age is 12 kilograms. And so this means that 5%, because it is a 5th percentile, so 5% of 36-month-old males weigh, and we're going to say less than 12 kilograms. So again, remember that the lower piece contains k% for that kth percentile of the data, so that 5%. And if you notice, this 95% is the 100% minus that 5% of 36-month-old males weigh, and instead of less than 12 kilograms, this is going to be more than 12 kilograms. The next example that we have says, the following data represents the pulse rates in beats per minute of 19 randomly selected students at a local high school. Find the percentile of the pulse rate of 71. So we need to find all the values that are less than 71. So going ahead and circling all the values less than 71. So again, less than 71. Do not count 71. And so we have a total of 6 that are below 71. So 6 are below 71. And again, we do not count 71. For percentiles, it is less than, back in the definition. And so we're going to take 6, which is the number that we have, divided by our total number, which again we had 19 students, and then times that 100% to get 31.58. And then we're going to round to that whole number, which is going to be our 32nd percentile. So again, rounding this 31.58 to 32%, which is the same thing as that 32nd percentile. Next we have is quartiles. So quartiles divide data sets into fourths, or 4 equal parts. So we have our first quartile, second quartile, and third quartile. So first quartile is denoted Q1. This is the bottom 25% of the data. Q2 is also called the median, and this splits the data in half. third quartile is going to be Q3, and this is the top 25% of the data. Another way to think of that is the bottom 75% of the data. So on the diagram here, we have things split into 4 equal parts. So this is our 25th percentile, or bottom 25%. We have our next 25%, the next 25%, and then that top 25%. And so you can notice we have our smallest data value, our Q1, Q2 are our median, Q3, and then our largest data value. These 5 values are going to come into play in just a moment. But in order to find these quartiles, we've talked about how to use our calculator to calculate the median. The smallest data value and the largest data value are things you should be able to look at and figure out from the data set. But right below this are how to find these values by using a TI-8384 calculator. Right next to that is how to do it by hand, which you can look at on your own. But again, since we always use a graphing calculator, we are going to focus on using the graphing calculator for this. So first thing to do is we're going to hit Stat, Edit, and we need to enter in all the values into L1. Then we go to Stat, Calc, 1var stats, and hit Enter twice. This is also where we found our mean, and likewise our median and our standard deviation. We also now will notice that we are given Q1, which is quartile 1, and Q3, which is quartile 3. So there's an example right below this that says the following data represents pulse rates and beats per minute of 19 random students at a local high school. And again, those are listed there. It says find and interpret the first, second, and third quartile for the pulse rates. So we need to find Q1. Our second is also called the median. And then Q3. And remember, we used a capital M before for median. So in order to find these, we need to take our calculator and input in all these data into L1. On your calculator, you're going to select Stat, and enter on Edit, and enter in all your numbers into L1. Make sure that these numbers are inputted in correctly before you move on with the problem. Next, select Stat, scroll right to Calc, and select Enter on 1var stats. We do not have a frequency list this time, so you need to make sure that you clear the L2 if it's there still. And you should just say your listed numbers are in L1. So again, we only had one list of values there. If you have the older style calculator, you do not need to type anything after 1var stats. You would just select Enter. So Enter from here, and again, we get a lot of different numbers. This time we are looking for our quartiles, and so scrolling down, you'll notice that quartile 1 or Q1 is equal to 68. The median or quartile 2 is equal to 73, and quartile 3 is equal to 79, or that's also called Q3. So from the calculator, we get Q1 is 68, our median is 73, and Q3 is 79. It also asks for us to interpret these. So Q1 is going to be 25%. Remember, this cuts the bottom 25%. So 25% of the numbers or pulse rates are going to lie below Q1, so below 68. So we'll say 25% of pulse rates are below 68 beats per minute. And then we have our median, so we can say 50% of pulse rates are below, or you can say above, or you can say in between, something along those lines are below. We'll say 73 beats per minute. That splits that data in half. The next one that we have is 79. This is Q3. And so we can say 75% of pulse rates are below 79, or we can say 25% of pulse rates are above 79 beats per minute. The next definition that we have is called our 5-number summary, and this is of a data set and consists of the smallest data value, Q1, your median, Q3, and the largest data value, which is what we had listed right up above. So this is our 5-number summary. Again, that splits everything into those equal parts, those 25%. So the next example that we have says the data represents the weights of each of the 2015 men's U.S. soccer training camp members. Use the data to compute the 5-number summary. So the weights of these soccer players are listed right there. And in order to come up with our 5-number summary, we're going to have to take a moment and enter in all of this data into L1. On your calculator, you're going to go to Stat, select Enter on Edit, and enter in all the weights into L1, double checking your numbers to make sure that you entered in all those values correctly. Next, go to Stats, scroll right to Calc, select Enter on one of our stats. Again, this list of numbers does not have a grouped distribution, so we only have a list of L1 values, our weights, and so we do not have a frequency list. And so you do not need to have anything typed there, and then you also will not need to enter anything after one of our stats for the older style calculators. Select Enter and you get a lot of information. For this problem, we were asked to find the 5-number summary, and so your min X value is 135, Q1 or quartile 1 is 155, the median is 170.5, Q3 or quartile 3 is 180, and our max X value is 215. Those 5 values make up our 5-number summary. So from the calculator, we have our minimum X value is 135, Q1 is 155, our median is 170.5, and Q3 is 180. The largest weight that we have is 215. So when you write out the 5-number summary, we usually don't put those words in there. We just list it as a string of values starting from our minimum and working our way up to that max value. So we just write 135, comma 155, comma 170.5, 180, and comma 215. From our 5-number summary, we're able to create what are called box plots, which is our next definition here. And this is a graph created using the 5-number summary. It's also called a box and whisker plot. In order to have our box plot, we also use the box plot and the 5-number summary to calculate and see if we have any outliers. And in order to do that, we have to first calculate our interquartile range, which is also denoted IQR. This is the range of the middle 50% of observations, and this is Q3 minus Q1. So definitely a little formula you need to know. Outliers are an observation that is distant from all other observations, and it occurs either because of errors or something is an extreme observation. And this could be common with certain populations. So an example of what a box plot looks like is given right below. And you can see that we have our 5-number summary. This is going to be our lowest data value, Q1, median, Q3, and then our largest data value. And then you'll notice that there's some dots out here that say outliers. We'll talk about how to calculate and figure those out. And then also here's the interquartile range. That's that box that are on the box plot. And also they also call these box and whisker plots, where the box is given, that's the middle 50%, and the whiskers are stemming out from that box, to the left and to the right. So a way to check for outliers, we first need to calculate Q1 and Q3, which we have done already, and we use our graphing calculator to do that. And next we calculate our IQR, which is found by doing Q3 minus Q1. And then step 3, we're going to determine the fences. So fences serve as cutoff points for determining outliers. And so these are our formulas that we need to know for our exam. Our lower fence is going to be Q1 minus 1.5 times the IQR. And our upper fence is going to be Q3 plus 1.5 times the IQR. If a data value is less than the lower fence, greater than the upper fence, then it is considered an outlier. If you think about those fences as keeping all the data values inside, in between those two fences, and anything outside of those fences, so anything smaller than your lower fence or larger than your upper fence, those are outliers, extreme data values. So we have an example right below this that says Anne collects data from the past 12 days on the number of phone calls she receives at work. The number of phone calls are, and there's a list of phone calls on there, determine if an outlier exists in the data. So again, in order to do this, the first thing we need to do is calculate Q1 and Q3. So we can do that by taking all of these data values and inputting them into L1. From the calculator, we get that Q1 is equal to 11 and Q3 is equal to 14.5. The next thing that we need to calculate in order to figure out if we have an outlier is our interquartile range, which is found by taking Q3 minus Q1. And again, remember, this is that middle 50%. So this is going to be 14.5 minus 11, which is 3.5. And then we need to calculate our lower fence, which I usually just call LF, which is found by taking Q1 minus 1.5 times the IQR. And so Q1 is 11 minus 1.5 times 3.5. Working this out, we arrive at 5.75. We also need to calculate our upper fence, which from the formula up above is going to be Q3 plus 1.5 times the IQR. Q3 is 14.5 plus 1.5 times 3.5. And working this out on your calculator, you get an upper fence of 19.75. So this means that your data values need to be between 5.75 and 19.75 for them not to be an outlier. So if you look at your data value, do we have anything smaller than 5.75 and anything larger than 19.75? So looking at your string of values, you will notice that you have an issue. That issue is arriving in 22. That is larger than 19.75 or your upper fence. So 22 is an outlier. And the reason why is because this is larger than your upper fence. In order to do a box plot of this, we will have to figure out how to do what's called a modified box plot. And we will work on this together with a worksheet. So the next thing is how to draw our box plots. And again, if we have an outlier, we will have to do a modified box plot, but we will look at that later. So the first thing is to draw a box plot. We need to determine our upper and lower fences. We need to draw a number line long enough to include the min and max values and also those fences. We put vertical lines in it, Q1, the median, and Q3. And then we are going to make a box that connects that Q1 to Q3 and our median in the middle. And then extending out those whiskers to our minimum value and also to our maximum value. And so this is going to be how to create a box plot. The next example says, from the previous example about the U.S. men's soccer team, create a box plot for the data. So we already came up with a 5-number summary for the men's U.S. soccer team. And so our 5-number summary was minimum value is 135, Q1 was 155, median was 170.5, Q3 was 180, and our max value is 215. So in order to make our box plot here, we need the 5-number summary, but we also need to find our fences. So don't forget about the fences. In order to find our fences, we need to calculate our interquartile range, which again is Q3 minus Q1. So 180 minus 155, which is 25. And then to calculate our lower fence, we're going to do Q1, which is 155, minus 1.5 times that interquartile range. And working this out, we get 117.5. And likewise, our upper fence will be Q3, which is 180, plus 1.5 times 25, our interquartile range. And this is 217.5. So next, looking at your data, which you can either go back to on the previous page, or you can look at your minimum value, which was the smallest weight, and your maximum value. So again, this is our max, and this was our min. So do we have anything smaller than 117.5 or larger than 217.5? And since our min is 135 and our max is 215, this means that we have no outliers. So nothing is outside of those fences. So in order to create our box plot, we need to draw a number line that is long enough to include our fences and also our 5-number summary. So our lowest fence is 117.5. So I'm going to go ahead and count by tens. So I'll say I'll count starting at 110, 120, 130, 140, 150, 160, 170, 180, 190, 200, 210, and then 220, which should be enough for this. Make sure you label your axes always. This is weights, and we're measuring these in pounds. So from here, I'm going to go ahead and do my box plot first, and then I'll put on my fences. So the minimum value that we have is at 135. And box plots just kind of hover above that axis. They don't actually touch it. So 135, Q1 is at 155. Then we have 170.5, 180, and then 215. So you should have 5 lines here. This is going to make your 5-number summary or your box plot. And again, those middle part make our interquartile range, which is Q1 to Q3, that middle 50%. And then we're going to extend out to our minimum and maximum value, those whiskers, which are horizontal lines extending from Q1 to the min value, and then Q3 out to our max value. Next thing that we need to do is put in our lower fence and our upper fence. And for these, we use brackets. So our lower fence is at 117. And again, this is our lower fence. And then our upper fence is at 217.5, which is really close to our max value. So this is our box plot, and also has our fences. And usually when you do a box plot, you also need to find your fences. Right below this, it says a box plot can be often used to identify skewness. So skewed is if a distribution is not symmetric and extends more to one side than the other, like we saw before, skewed left and skewed right. And so there are 4 different diagrams there. There are histograms, and then right underneath it are a box plot. You can see that there are outliers listed on some of them. You can see the skewedness on some of them also. And you can see that when the data is more bell-shaped, it has a smaller box, that interquartile range, like the first one, whereas that second histogram is more spread out, more dispersed, and so is that box on that interquartile range in the middle 50%. So we have another example here, And this one says we would like to compare two distributions by using box plots. A potato farmer in Idaho tests two different types of fertilizers on his crops. The table shows the yields in kilograms of potatoes from fertilizer A and fertilizer B. Investigate the effects of the two fertilizers on potato growth. So since we have two sets of data, we have it for fertilizer B and fertilizer A, we need to both, for these individually, calculate our 5-number summary, and I'll go ahead and draw a line here, for fertilizer A and also for fertilizer B. So we're going to go ahead and calculate our 5-number summary for both, and then from there we can take those values and find our fences and determine if we have any outliers. And then from here, we need to draw, down here in part A, it says draw a side-by-side box plot for each fertilizer. So for fertilizer A, you need to put in all of these values into your calculator. And I'll do this one for you, and then we will try fertilizer B together. So our 5-number summary for fertilizer A is going to be 16, 18, 19.5, 22, and 27. So now we're going to go ahead and try fertilizer B. So take a second to input these values into L1, and then write down your 5-number summary that you get from your calculator. For fertilizer B, we're going to go to Stat, enter on Edit, and enter in all of our numbers into L1. Double check to make sure you have your numbers entered in correctly. Next, we're going to go to Stat, scroll right to Calc, select Enter on OneVar Stats. Again, make sure that frequency list has nothing entered there since we just have a list of numbers. Select Enter, and our 5-number summary is going to show up. Our min value would be 18, quartile 1 is 20, median is 22.5, quartile 3 is 27, and our max X value is 29. So from the calculator, we get the 5-number summary for fertilizer B is 18, 20, 22.5, 27, 29. From here, we can calculate our interquartile range for both of these, and then also our lower fence and our upper fence. So fertilizer A, our interquartile range, 22 minus 18 would be 4. And then our lower fence is going to be 18 minus 1.5 times 4, which works out to being 12. And our upper fence is going to be Q3 plus 1.5 times that interquartile range, which works out to being 28. And so from here, using 12 and 28 and looking at your fertilizer A data or at your 5-number summary, do we have any values smaller than 12 or larger than 28? And if you look at that, you'll see that the answer is no. So that means we have no outliers. Again, the reason why is because your data is between your lower fence and your upper fence. So all the data is between 12 and 28. So now we need to do the same thing for fertilizer B. Q1 is 20 and Q3 is 27, so our interquartile range will be 7. Lower fence is going to be 20 minus 1.5 times 7, which works out to being 9.5. And our upper fence is going to be 27 plus 1.5 times 7, which works out to being 37.5. So again, looking at these, do we have any values that are smaller than 9.5 and larger than 37.5? And again, we're looking only at fertilizer B. And no, there's no values that are smaller than 9.5 or bigger than 37.5. So this means that we have no outliers here also. So we're going to take all of this data and we're going to create what's called a side-by-side box plot. And so in order to do this, we need to make a number line that's going to be long enough, include all the numbers for both box plots. And so for this, the smallest value that we have out of all of these would be this lower fence of 9.5, and the largest value that we have would be our upper fence of 37.5. So I'm going to count by fives, and I'm going to go from 5 out to 40 on my number line. And again, if you want to count by something different, you definitely can. And this is yields of potatoes. So I'm going to go ahead and do fertilizer A first. And so the 5-number summary of fertilizer A was at 16. Do the best you can on this. Q1 was at 18. 19.5 is our median, 22, and then 27. So again, that middle part makes our box. And then extending out. And the last thing we need to add in is our lower fence and our upper fence. The lower fence was at 12. The upper fence was at 28, which is right by that last one. Now we need a way to show that this is fertilizer A, because fertilizer A could be done first or second. So we label that by putting fertilizer A on the sides. So now we're going to do this again, but for fertilizer B. So the 5-number summary that we have is at 18. And you're going to have this one float above the other box plot. And then at 20. And then 22.5, 27, and then 29. And again, those middle 3 lines will make our interquartile range, extending your lines out to form those whiskers. And then the last thing that we need to put on here is our lower fence and our upper fence. Lower fence is out at 9.5, and the upper fence was out at 37.5. And again, labeling this fertilizer B. So it doesn't matter if you had fertilizer A on top or on bottom. Just make sure that you have them labeled over on the left side. So there's some questions right below this that pertain to these box plots and the data. So B says, does there appear to be a difference in the yield of potatoes between the 2 fertilizers? And we would say yes. It looks like fertilizer B is more dispersed. That box is larger. And I would also say, looks like fertilizer A is kind of skewed to the right since it has a longer tail going to the right. So is there a difference? And yes. And you can put down whatever reasoning is that you think. You can say that the interquartile ranges are different. The values, the median for fertilizer B is larger than that for fertilizer A. A lot of different things you can put down. Part C says, does one kind of fertilizer have a more consistent yield of potatoes? And we'll say yes. And consistent would mean that it wouldn't be so dispersed. And so looking at this, you would say fertilizer A is more consistent. And we could say because the IQR, our interquartile range, is smaller. And again, like we saw with those histograms and matching with the box plots, that when the data is more dispersed, it has that wider IQR.